All right. Probably the last couple of house cleaning type deals. Whether you did 4-1 or 4-1 not, 4-1 late will still show up. Just to make sure that's clear. I've got to ask that a couple of times. Like I turned it in and it's assigned to everybody. What it is 4-1 should disappear. I'm trying not to clutter up your stuff. And if you want to go back and look at something, then you can look at 4-1 late. Also, if you answer anything off of 4-1 late, I don't give you the grade off of 4-1 late if you did 4-1, right? So I look at 4-1 first and I put in the grade, and then I look at 4-2. And if, 4-1 late. And if 4-1 late's grade's higher than 4-1, I put that in. And if it's lower, I don't touch it. Y'all okay with all that? Okay. Basically, you got to get 80% or higher to get all 5 points. 4-point anything always bumps it up. 3-point anything will bump it up to 4. Point anything will bump it up to 1. So basically, you're not having to take the final, but you're not getting a whole lot of points for your homework. Okay with all that? Good? Happy? 4-1, 4-2. So I put 4-1 in the grade book. If it's an N, then I don't have it for some reason or another. If something like if it's a computer issue or something, we'll just make sure we communicate with that. Okay, like I said, this is all a learning process. I got 4-1 late still 5 points. So the first couple chapters, I'll still have the lates 5 points. At some point, I'll start bumping those down to 4 points max. Okay, so it's not that big a deal. It doesn't kill you. However, I think there need to be some repercussions for not doing it when you're supposed to do it. Okay. The hard deadline is test day. So whenever the test day is when I have them all due. So that's when you'll see that. You got till Monday. I wish I would have had my review stuff. And that way, y'all, as you're working on it, you would have had time to do all that. If you're bored sometime tomorrow or sometime later today, I should have it. And so if you want to come by and grab it, it's not, you'll have time Monday, but our test is going to be Wednesday, right? So because we have so much long, if you want to start reviewing or doing some things, we'll do some things in class and we'll talk in class. And then basically I just give you the rest of the time to just work amongst yourselves and work as teammates, right? And try to get ready for the test that's going to be on Wednesday. Okay, I haven't made it yet. Got a good idea. I do make a new one every year, but I don't know. Last year's were pretty good. I probably won't change them up a whole lot. All right, everybody happy, joy. Good. Anything over 4.2 other than it being moving way too long? That's probably the longest assignment all year, and I apologize for that. I probably could cut that back quite a bit. It got to be pretty bad. 43 is a lot of questions. Was it 43, 46, whatever it was? A lot of questions, and not only was there a lot of questions, a lot of freaking reading. Told y'all signed up for a math class, so I have to remind y'all that. Yeah. Good? Happy? I'm going through this one blindly. I haven't looked at this one since last year, so we'll see how it goes. I don't remember. Using studies wisely. I don't think there's much on this. I think we've talked about everything on the chapter, I think. When members of a sample are selected at random from a population, we can use the sample to judge things about the population. So that's what statistics is. We kind of mentioned that several times, right? When I take a sample at random, I can judge to the entire population, provided the sample represents the population, okay? That is, we can make inferences. That's inferring to the entire population. That's what that's what statistics does, right? We use samples to infer to the population. Which the sample was randomly selected. Inferences come from convenient samples or voluntary response samples will be misleading because these methods of choosing samples are biased, right? We talked about that in 4.1. We're almost certain that these samples do not fairly represent the population. We also talked about volunteers. Be careful with that, right? Volunteers are okay to use. They'll use volunteers all the time, but just remember that your volunteers will only deduce to that kind of population, okay? Sampling variability. Here's a definition of it. This is like a really duh factor. Again, these are things that we're starting to get into our heads about what statistics is. Sampling variability. Different samples of the same size from the same population produce different estimates. We'll really hit this hard in chapter 7. So this is just something really that's leading us into it. I don't think there's anything on the test about this. But this is something, again, just to kind of get our mind wrapped around this. This should not be a foreign concept. Sampling variability. Sampling variability. So we know what sampling is, right? Sampling is getting information or getting a sample or getting a part of the population. And then variability varies. It varies. So let's just put it in real perspective right here. Okay, you guys are my population. You guys are my population. I'm going to take a sample from that population and I'm going to get a sample of 3. So I'm going to get 3 of you cats. So I'm going to throw all your names in the hat and I'm going to pull 3 of them out, right, without putting them back in. I'm going to get the GPA of those 3 cats. Okay, y'all good with that? All right, so I got their GPA, 3.75. Throw all the names back in the hat, pull out 3 names. Am I going to pull out the 3 same names? Maybe, probably not, right? Chances are really good it probably won't be. So I'm going to get 3 different names. Again, I might get the same, but let's just say I get 3 different ones. One of them might be the same. 2 of them might be the same, but let's just say they're different. I'm going to get that GPA. Is that GPA going to be 3.75? Probably not, because each sample will vary from sample to sample to sample. Duh, right? I mean, if it was the exact same, I'd be more surprised if it was the exact same than if it was different. I'd be surprised if it was 3.75 and 1.25. I'd be surprised about that. But I'd probably be more surprised if it was the exact same, because I don't think that chances are very good for that. Y'all good with all that stuff? So each sample varies from sample to sample to sample. And that's something that we're really going to hit hard. I think it's chapter 7. Chapter 7, we really start talking about this sampling variability, okay? Larger samples tend to produce estimates that are closer to the true population than smaller random samples. Again, this is not going to be on this test, anything about this, but this is kind of stuff in general that, again, we want to start wrapping our heads around what this course will do. Larger samples tend to produce estimates that are closer to the true population than smaller samples. Larger samples tend to produce estimates that are closer to the truth population. Larger samples produce the values that are closer to the population than smaller samples. So here we go again. We got you guys as my population, and I'm choosing a sample of 3. And you guys, I'm going to get 3 people's grade point average. I'm going to get the average of those 3. Let's say that one of those 3 has taken every single AP course in the world, taken 18,000 college classes, and they have like a 6.0. Well, the other 2 are going to kind of bring that 6 point down, right? But that 1.6 is going to bring those other 2 fairly high up, right? That's with a sample of 3. If I got a sample of 8, now that 6 is going to bring that down closer to, I don't want to say reality, but closer to what the class is, okay? That outlier, if you will, or that really high grade is not going to affect all the other as much as if it was a smaller set, right? That's mathematics. That's mathematics, right? If you have an 80 and an 80 and an 80 and an 80 and a 90, that 90 is not going to help a lot of those 80s. If you got a 60 and a 60 and a 60 and a 60 and a 100, well, let's just do it back the other way. Let's do an 80 and an 80 and a 90. Now the 90 is going to affect those 80s a little bit more than if I had 12 80s, right? So the higher sample you get, the closer to the truth you get. If I got all 30 of you guys, I would get the truth. However, it would probably be inaccurate because all of you would be a census, and we realize census are not very accurate anyway. Kind of good with all that stuff? Again, this is not going to be testable stuff. It's just stuff we kind of start thinking about. More precise. I did mention that word, right? Don't say more accurate. That's where students will mess up a lot of times. It's more accurate. No, No, if I'm getting your 3 GPA, it's not accurate or inaccurate. It is what it is. I mean, that's accurate value. That's an accurate value. Okay, it's not more accurate or less accurate. It's just accurate. It's more precise. It's closer to the population. It's more precise. So it has less variability the larger your samples have. Again, we'll really show this stuff in chapter 7, which doesn't happen until much later, right? What do I got here? Jar, M&Ms, beads, Skittles, etc. Okay, so I got a jar, I'm going off memory, with M&Ms in there, or beads, or Skittles, or whatever you like. A bunch of different colors. N is 20, so anytime you see N, a small N like that, that's your sample size. Okay, that's your sample size. So I'm getting 20 of those bad boys out of that jar. That's the percent of reds. Out of those 20, that's the percent of reds. So it looks like 30% happened the most. However, there was a couple of 10% and there was a couple of 50%. So out of those 20, 10 of them were red. But that only happened once. You're good enough with all this stuff, right? Seeing this? So I must have gotten 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I don't want to count them all. It looks like 50. I must have done this 50 times. So I got 50 of these out, and I figured out what percent of those sample was red. And I threw them all back in there, and I shook them all up, and I pulled out another 20. And I put them back in there, and so I did that 50 times, and there's my little, this is my little picture of those 50. Man, I forgot they did all this stuff this early. And then I got 100 out. So then I did it 50 times. Instead of getting 20 out, I got 100 out. Same scale. Same scale, 10, 20, 30, 40, 50. This one's a whole lot more precise. It's less varied. It's more precise. I don't want to say it's more accurate. It's just more precise, right? I got no 10s out here. In fact, I got no 20s, right? Because what? As my sample size increased, the 2 or 3 times I got a smaller set, it leveled out. Okay, y'all okay with all that stuff? So this is a sample size of 20, sample size of 100. It looks somewhat the same. It starts low, goes high, goes low. This starts low, goes high, goes low. But that one goes all the way up. I mean, that one had a 40 and a 50 and a 45 quite often. This one only had a 40. That's as low as it went. Beautiful. How much do national football players weigh on the average? A random sample of 50 players got an average of 244.4. Do you think that 244 is a true average of all NFL players? I'd be really surprised if that was the exact average. Okay? No, different samples of size 50 is going to produce different averages. It would be surprising if this estimate is equal to the true of all of them. Okay? I mean, this is really, really common sense, but again, these are things we kind of start wrapping our head around what statistics is and what it does. And that's why we like to get good samples, because bad samples, we know that that value is even further off. It's even further off. So how would I want to get a better sample? Well, I probably want to stratify by position. Make sure I get some linemen, make sure I get some receivers, make sure I get some quarterbacks, make sure I get some running, make sure I get certain positions. That way I know for a fact we're all covered. Because my sample of 50 could all be linemen. And if they're all linemen, that's going to overestimate it. They may all be receivers. That's going to underestimate it. Okay? Which will be more likely to give an estimate closer to the true average, a random sample of 50 or a random sample of 100. And we understand that that would have to be the random sample of 100. Because if you got 2 receivers in the sample of 50, that's affecting the 50 more than it would be the 100 if I had 4. A random sample 100, larger samples produce less variability than smaller samples. Y'all okay with what all I'm talking about? Again, really this has nothing to do with sampling, but it's just statistics. Okay, beautiful. Well-designed experiments allow for inferences about cause and effect. Now, that's a big deal, and I kind of mentioned that on Monday for you guys. Well-designed experiments can show cause and effect. Observational study cannot. A bad experiment cannot. But if it's a well-designed, well-performed experiment, we can show cause and effect. Statistically significant. We mentioned this day one, where we started talking about likely to happen or unlikely to happen. We said 50% is that midpoint. 51's likely to happen, 49's not. And then we decided, wait a second, if there's a 30% chance you're going to break your arm, that's pretty likely now, right? So we dropped that thing down to 5%. Okay? When the observed results, I gave you a note packet, didn't I? No. I'm an idiot. When the observed results, so that's the value we get, right, of a study are too unusual to be explained by chance. Too unusual to be explained by chance. It's statistically significant. Statistically significant. I still got to do the calendar. Statistically significant. When basically my sample is so far off, something's wrong. Something's wrong. All right, here we go. Again, big picture stuff. None of this is on your test. Why am I talking about it? Because it's freaking important. I know for a fact the GPA of this class is 3.92. I don't know that. I'm making that up, but let's just say that, okay? Bunch of smart kids in here. We got 3.92. I get a sample. I would expect that sample to be close to that. I would expect it to be close to that. How far do I start thinking that it's a bad sample? I don't want to say bad sample, a bad number from that sample. Because if I throw all your names into a hat and pull out 3, it's not a bad sample. It's just how far do I have to start thinking? Well, if I happen to get 3 cats that have a very low GPA, it's not going to happen, but again, just play along, at a 1.67, that's probably statistically significant. One of two things happened. One of two things happened. I got a really bad sample. Or that's a lie. One of those two had to happen. That's really a bad sample, or I'm lying. If I got another sample and it was down here, and another sample and another sample down here, now I'm starting to really believe that's a lie. I didn't get a bad sample. And that's why we take good samples. Because if we take good samples, now we're starting to think, that's a lie. Can we still get a bad sample? Could. Right? Could. But that's statistically significant. When the observed results are too unusual to be explained by chance alone, it's so unlikely for that to happen if that's true. That's statistically significant. Is talking on a cell phone while driving more distracting than talking to a passenger? So picture yourself in a vehicle talking on a cell phone or talking to a passenger. David Strayer and his colleagues at the University of Utah designed an experiment to help answer these questions. They used 48 undergraduate students as subjects. The researchers randomly assigned half the subjects to drive with a simulator while talking on the cell phone. The other half to drive the simulator while talking to a passenger. So I don't know how we rather gather these cats, but we randomly assign them into 2 different groups. Okay? Half of them got the passenger, half of them were told to talk on the cell phone in a simulator. So my guess is that's kind of nice because the simulator is probably putting them through the exact same course. Okay, so controlling the environment. And that's what we want to try to do. We don't want to actually tell them to do it on a car because your car might be a distraction. The street, the other cars might be a distraction. But if I put them in a simulator, now I've helped control all that stuff. One response variable was whether or not the driver stopped at the rest area that was specified by the researchers. I want you to stop at this rest area. before the simulation started. The table shows the results. So y'all kind of picture all this stuff, see what's happening. Here's the results. Here's the cell phone. This is the treatment, right? Treatment or the factor. Here's talking on the passenger. There were 48 of those cats. There were 24 here and 24 here. Half and half. 12 of these. This was 12 and 12, and this was 21. Holy cow. That looks kind of statistically significant. These 12 stopped, these 12 didn't stop. These 21 stopped, and these 3 did not stop. That's a pretty big difference. This is 33, and this is 15. 33 actually stopped, and 15 didn't stop. That's kind of big. Man, they must have really, if you really had to go to the bathroom, I bet you had a more chance of stopping. Calculate the difference, passenger minus cell phone, in the proportion of students who stopped in between the two groups. So who stopped? Y'all okay with that? 33 out of the 48. Good enough for that? 33 out of the 48 stopped. I'm hoping that that's what that number is. Passenger minus cell phone. Oh, I'm sorry. They didn't want the total. They wanted, that's minus. I thought it was passenger to cell phone. Minus. So here's the passengers. Here's the cell phones. So 21 out of 24, 12 out of 24. So what do we have? 12, 9 out of 24 difference. 9 more stopped with a passenger or 9 less stopped with a cell phone. We're talking, we got fractions, you got decimals, you can put all this stuff however you want. They don't care. They don't care if you leave it a fraction. They don't care if you turn it into decimals. They don't care if you put it into percents. Most time we hardly ever put things in percents because you'll get tired of writing a percent symbol. You'll see some questions like this, I'm thinking. 100 trials of simulation were performed to see what differences and proportions would occur due to by chance alone a random assignment, assuming the type of this. 33 stoppers, 15 non-stoppers were randomly assigned to 2 groups of 24. I don't know what all we're doing here. What's all this? Oh, okay. All right, so here's what happened. Here's what they did. Play along. They assume that there's no difference between talking on the cell phone and talking to passengers. They assume there's no difference. So they did a simulation. They did a simulation. So if they thought that there was an equal chance of that happening, or I'm sorry, we had 33 people that stopped and 15 that non-stopped, okay? If that was the truth, happened, right? We're randomly selected 24, there's 3 dots at 0.29. Okay, so what was our percentage? 0.375, right? There's 3 dots, one more. There's 3 dots at 0.29. Explain what those 3 dots mean. Okay, so in my simulation, 3 times the difference was 0.29. In my simulation, because these are 100 dots, right? 100 trials of simulation were performed to see what the differences would occur due to chance variation, assuming it did not affect each other. So if we're assuming it did not affect each other, the difference should be 0. Okay? So the difference should be 0. That's why this is the highest and these are the higher ones, and that's why this over here. But 3 times the difference was 29%. 3 times the difference was 29% out of my simulations. 2 times it was 29% the other way. 1, 2, all these times it barely had a buried chance. Okay? So 3 times there was a difference, or it happened a difference of 29%. When we assumed that there was no difference, there were 3 simulated random assignments, or 3 samples, where the difference was 0.29. What was our difference? 0.35? Holy cow. 3 times out of those 100, it was 0.29. We ended up over there. Statistically significant? That should not have happened. If this is true. If that's true, that should not have happened. Would I expect this to happen right here? Yeah, it happened 3 times. That's still pretty darn low. 3%. Right? Well, we always talk about that 5%. Here, I kind of started expecting this stuff to happen. I expect, not really expect. And I don't expect anything on the other side of that. Y'all okay? Use the results of simulation to determine if the difference is statistically significant. It absolutely is statistically significant because in none of my simulations do I have a 0.35. I don't have any. So because 0.35 never happened in my simulation and it happened in real life, I do think there is a difference. How about that? I do think there's a difference. This is assuming there's not a difference. All of these should show up in all my simulations. I never got that. I never got close to that percentage. Y'all okay with what I'm saying? Good? It should not have happened. It did. So because it did happen and it should not have happened, given this scenario, I've got to assume that that was statistically significant. If my number was right here, that's not statistically significant. That should have happened. That should have happened. Anything here should have happened because, that's how many times it happened. It happened that many times through there. Anything outside of that should not have happened. And this is iffy. Like, it did happen 3 times, but 3 is starting to become iffy. Even though we got it, it's not likely. Because a difference of 0.35 or greater never occurred, the difference is statistically significant. It's very unlikely to get a difference this big, assuming there's no difference. Like, I should have got 0 more times than E. Now, it doesn't look like I ever got 0, but I'm guessing because of numbers, I don't guess I could have ever got exactly 0. We got real darn close, though, because that's just 0.1. Yes, no, maybe. You'll get some questions like that tonight. Again, none of this is like on your test stuff. We're just kind of getting started. Random selection of individuals about the population. Is that on your notes? Did I leave a blank or something? You just have to fill in something. Random selection of individuals. Random selection allows us to make inferences about the population from which the individuals were chosen. If we don't do random selection, it's probably going to be a biased selection. Okay, we need it random somehow. Stratified random, cluster random, systematic random, simple random. It's got to be random. It's got to be random. Voluntary is not random. Convenience is not random. Random assignment allows for inferences to show cause and effect. So let me break these 2 statements down for you again. Let's break these 2 statements down. What I tell you about volunteer, it happens a lot, right? Volunteer takes off this one right here. So volunteer, I really can't judge to entire populations. I can only judge to people like them. So if they're all 18-year-old males, I can judge to 18-year-old males provided they're representative of the population. Okay? So, but if I do random assignment, I can still show cause and effect. But I can only show cause and effect to people like that. If I random select, and I just learned something about it, that's an observational study, I can't show cause and effect. If I random select and random assign, then I can show cause and effect to that population. They're kind of okay with what they're saying. Again, just some homework questions that you're going to see, kind of wrapping us around it. Were they randomly assigned to groups? Were they randomly selected? You got a yes and a no and a yes and a no. Y'all with me on my little table? So if they were randomly selected and they were randomly assigned, I can make inferences about the population and I can show cause and effect. I can do both. If I only want to make inferences about the population, that's all I need. If I want to make inferences about the population and show cause and effect, I got to do both of those. If they were randomly selected, I can make inferences about the population. However, if I did not do random assignment, I cannot do cause and effect. Okay? And this is what we do a lot in statistics. We take random selections. We don't always do random assignment. So because I don't do random assignment, I can't show cause and effect. I can just learn something about the population. Okay? And I can make inferences to the entire population. This is a no, and this is a yes, and of course that one's a no and a no. Y'all okay with my little table? Good enough for all that stuff. So as you're reading any scenario, make sure you recognize, was this random selection? And if it's an experiment, was it random assignment? And it can be, I almost said stratified, it can be blocked, right? As long as it's randomly done, you're okay. All right. Guys, I hope you can explain the concept of sampling variability when making inferences about the population. Sampling variability, different samples produce different values. Explain the meaning of statistically significant. If you can start understanding that now, the chances of me getting what I got are really small, and it happened. That's statistically significant. It should not have happened. I should not get a grade point of 1.6 provided that the average is 3.92. Shouldn't happen. So they're going to give you some type of simulation, Typically, it's going to look mound shaped and it's going to have an average around in here, and it's going to have very unlikely to happen and very unlikely to happen. And if you're outside of that, it's really, really unlikely to happen. And if you're inside of that, you would expect it to happen. Identify when it's appropriate to make inferences about the population, random selection, and when it's appropriate to make a cause and effect, random assignment. Evaluate if a statistical study has been carried out in an ethical manner. I don't know what that means. I need this button. I need this button.